Random variables and probability distributions. Let's start off by talking about discrete and continuous random variables. First of all, what is a random variable? A random variable takes numerical values that describe the outcomes of some chance process. So this is probability. A random variable is essentially a random process that can take various numerical values, right? A probability distribution of a random variable gives all of its possible values. So for example, tossing a fair coin 3 times, let's say x, the random variable x, capital X, is going to be the random variable that represents the number of heads obtained in flipping a coin 3 times in a row. The probability distribution would give all of the potential outcomes of that. So we're looking at flipping a coin 3 times. We have 4 different possibilities, right? We can flip the coin 3 times and get heads 0 times, so x would equal 0. We can say that we get heads once. That can happen 3 different ways, either on the first flip, the second flip, or the third flip. We can get heads twice. That can happen either the first 2, the first and third, or the second and third. Or we can get heads all 3 times. That only happens in one scenario where we flip in a row. So the random variable x can equal 0, 1, 2, or 3. The probability that x equals 0 is 1 out of 8, because there are 8 total outcomes here. The probability that x equals 1 is 3 out of 8. The probability that it equals 2 is 3 out of 8. And the probability that it equals 3 is 1 out of 8. And we can graph this using a simple histogram style graph. Or we could leave it as just this table giving us the value and the probability. And that is a probability distribution for a random variable. Easy stuff. Now, the example we just looked at was a discrete random variable. A discrete random variable takes a fixed set of possible values with gaps in between. The probability distribution of a discrete random variable is going to list all of the probabilities for each of its potential values, and it looks like this, basically. So this is an example of a discrete random variable with its possible outcomes, right? And a lot of the things that we think about fit in this category. This is a very common category for us. Some key things that we know based on our last subunit: every probability must be between 0 and 1, and the sum of all of the probabilities have to add up to 1, because that's how probabilities work, right? If we look here, the probabilities are all between 0 and 1, and if you added up all of these probabilities, you would in fact get 1, which makes sense. If you add them all up and you don't have 1, then you're missing something. If you're trying to make your own probability distribution, a random variable distribution, you basically just list all of the values that it can take, and then you list all of the probabilities of each of those values. It's pretty easy, to be honest. It's easy for discrete random variables anyway. Now, when you're trying to find the mean for a discrete random variable, it does get a little bit more complicated, but we have the calculator to help us out. And I'll show you how to do that here in a moment. So you have all of the values that it can take, and then you have each of the probabilities for those values. If you're trying to find the expected value, or the average or the mean value for a random variable, what you do is you multiply each value by its probability, and then you add it all up. Not too complicated. So for example, in this word problem, they have APGAR baby test scores, where apparently babies can score a test between 0 and 10. I don't know anything about testing babies. So let's say the random variable is the score that the newborn baby can make on the test, and the probabilities are as follows, right? We have all of these different probabilities. Apparently it is likely that they score an 8 and a 9. It's less likely that they score below or above that. So if we're going to compute the mean for the random variable and interpret it in context, here's what we would do. So first of all, we'd add up each of these values, and I don't really feel like doing that by hand, so I'm going to use the calculator. So yeah, like I said, I'm not going to plug in each of these and add them all up, because that just takes too much time, and I don't really feel like it. So I'm going to show you how you can do it on the calculator. If you are doing it by hand, though, it is a pretty straightforward calculation. It's just very tedious for long lists, right? So the scores, the potential scores, I'll list in this one. And the probabilities that go with them, I'll list over here. And there you go. We have them all listed, right? So the way we calculate this is very similar to what we've done in the past, right? We have one random variable. I know we have two lists, but we have one random variable. That is the score, the baby's APGAR score. APGAR score. It has varying probabilities, but these are not different variables. The probability is not its own variable, right? The probability is associated with the random variable, the score. So we have to treat that as if it's associated with it, and there is an easy way to do that. So when we do our one variable statistics, just like we've done in the past, we have one list. I know we have two, but really we have one. We're finding the score, the frequency, right? So frequency, remember, that's how often something occurs. Well, that's our probability. So we use the probability as our frequency list, and then it will tell us the average score for this probability for this variable. Instead of adding up all of these, it says, oh, you already know how often these happen. I'm just going to use what you told me and add them all up that way. So there you go. So now that we've added them all up, apologize for having to go back and fix the typo, we see that the mean is 8.128, meaning on average, the score a baby will make on its APGAR score or test will be 8.128. Or any new baby taking a test, the expected score would be around 8.128. Now, the standard deviation is a little bit different. Now that we know the average score, we take each of those values, 0 minus 8.128, 1 minus 8.128, and so on, square all of them, multiply each of them by their respective probabilities, and then add them all up, and that would tell us the variance. And so if the variance is 2.066, then the standard deviation would be 1.437, meaning that even though the expected score is 8.128, on average, any individual baby will score 1.4 points away from that in either direction. So if we look at our calculator, we can see, if we know where to look, there's our standard deviation there. Same standard deviation that we had before. It doesn't give us the variance, but if we needed the variance, we could just square this value, right? And since this is a probability distribution, it doesn't make sense to look at the sample standard deviation. We don't have a sample size, right? This is just a probability distribution. So there you go. Now, for continuous random variables, we have to behave a little bit differently, right? So a continuous random variable, x, takes on all values in an interval of numbers, right? It's not just going to be 0 or 1. It could be 1.5. It could be 1.78. It could be the square root of 2. It could be pi. It could be any of those numbers, right? Integers, real numbers, irrational numbers, any of them. So when we're looking at continuous random variables, the probability distribution for those are considered a density curve, right? And we've already seen one. We're very familiar with one. The probability of any event area underneath the density curve and above the values of x that make up that event, okay? So we're looking at portions of the area of this curve, and that's going to give us the probability. Again, hopefully this is starting to ring some bells. The probability model of a discrete random variable x assigns probability between 0 and 1. However, a continuous random variable has infinitely many possible values, so it does not make sense to look at any one probability or any one value and calculate that value's probability. Rather, we look at intervals for positive probabilities. If you're looking at something that has infinitely many possible values between a range, then if you pick any one value, the probability of getting that, all of you calculus people will understand, the probability of any one value is, infinitely close to 0. It becomes 0. the closer you get to one single value. So we don't look at individual probabilities, we look at ranges of probabilities for continuous random variables. Now, the density curve that I was referencing, that I said hopefully rings some bells for you, is the normal curve, right? This is a curve that we can calculate probabilities with, and as of right now, as of this moment, in this subunit, this is the only one that we're familiar with. So when we're looking at normal densities, normal distributions, we can calculate probabilities of things occurring within those distributions. And the good news is you already know how to do that because the way we do it is the same as how we did it back in Unit 1. So let's look at this example. The heights of women closely follow the normal distribution with a mean of 64 and the standard deviation of 2.7. So if we choose one woman at random, we'll say her height is capital Y, right? So Y is the event of, if we repeat the random choice many times, the distribution of Y is going to be the same normal distribution that describes the heights of young women, right? And that's a statement that we have to put in there just to make sure that we are. In statistics, it becomes necessary to prove that what you're doing will follow whatever distribution you're using to solve it. So in this case, because we are drawing from a normal curve, or drawing a random person from a normal curve, we kind of have to say that if we did this a bunch of times, it would also follow the normal curve, because duh, but it's something we have to say, right? So we can then ask, what is the probability that the woman that we drew at random has a height between 68 and 70 inches tall? Well, we do this the same way we've done it before. If we're going to do it by hand, then we use the z-scores to calculate those two ranges, subtract them from one another, and then we have our probability, right? I'm sorry, we don't subtract the z-scores. We subtract the p-values that go with them, right? So we can calculate the z-scores here. So 68 minus 64 over 2.7. Value minus mean over standard deviation gives us the z-score for that. And then value minus mean divided by standard deviation gives us the second z-score. The probability we're interested is the area of the curve that is between those two z-scores. And I'm not going to pull up the normal table. Well, I guess we could look at this. So the z-score for this minus the z-score for this will give us, the probability that's here minus the probability that's here would give us this probability in the middle, right? So when we find those two in the normal table, we can subtract them and we get this probability. So the probability of drawing a woman at random whose height is between 68 and 70 inches tall is 0.0562. That's pretty easy. We can also use the calculator like we've done in the past. This is a normal CDF, right? So we can say we're still using normal distributions, so normal CDF. The probability that her height is between 68 and 70 inches, given that the average height is 64 inches and the standard deviation is 2.7 inches. And there you go, there's the probability. Likewise, you can also use the online statbook calculator or the Alcula calculators that we've used in the past. They work the exact same way. You have your two values. You're obviously looking for between 68 and 70. You're given the probability, right? Same deal here. Now, in the past, I would have taught this separately as its own subject, but it is part of this subject in this subunit, so we're going to keep going. We're going to push through it. It's actually pretty straightforward stuff. So it says we did this, but we didn't. We would have done it in Chapter 1, first of all. Second of all, we just didn't do it because it didn't make sense to do it at the time. We mentioned it, but we didn't really test over it at all. So one thing that we should know is that when we add or subtract a constant to each observation in a sample, right? So if I say, if I'm talking about these women's heights, if I said, okay, well now every woman is standing on a 6-inch tall platform, what are their heights? It makes sense that not only would each observation increase by 6 inches, but it would also add 6 inches to the mean, or the center of that distribution, but it wouldn't change the shape or the spread, right? It wouldn't change the standard deviation. They would still vary by the same amount. It's just everything would be shifted a little bit to the right, a little bit higher. If we multiply each of the observations by a constant, which I don't know how that would translate for height measurements, but whatever. Maybe we convert to centimeters from inches, or we convert to feet. Now let's convert to centimeters. So if we multiply everything by 2.54, then that would obviously change the center by multiplying it by 2.54. We would also have to multiply the spread by the absolute value of 2.54, which if it's positive, obviously it'll still be 2.54. But if we're multiplying it by a negative value, it still will get more spread out positively. You can't get a negative version of spread out. If you're getting less spread out, then you're multiplying by a fraction. But it still wouldn't change the shape. So if it was normal beforehand, it will still be normal. So these two things are important to understand. If we add something to this curve or subtract it, it would literally shift it, but nothing else would change on it. If we multiplied this by a value, then the shape would be the same, but it would get more spread out or less spread out if we're multiplying by a fraction. And of course, the center would also be multiplied by that same value. So the center would move, shape would remain normal, but the spread would change by whatever factor we're multiplying by. Those are some pretty intuitive things, to be honest. That's why I didn't spend very much time on it. The same is true for random variables and probabilistic distributions. If we have these two distributions, right? Well, let's just use the example to talk through it, right? So the two distributions at the right show two random variables collected by Pete's Jeep Tours. X is the number of passengers on any given day, and C is the amount of money that he collects from each passenger, right? So here's the passengers, and here's how much money he collects, right? Obviously, these are being multiplied by 150. The probabilities aren't, but the values for X are. We see that the shape and the spread have changed, but we see that the center and the spread have changed. This one spreads from 2 to 6. This one spreads from 300 to 900. The center here is at 4. The center here is about 600, but the shape does not change, right? So multiplying by 150 has changed the center and the spread, but not the shape. If we say, okay, well, now he's got to subtract out $100 for gas, then what that does is it changes only the center. The shape and the spread have remained the same, right? The center went from 600 to 500 because everything shifted to the left by 100, but nothing else has changed about this density curve, nor has it changed about the distribution. Now, the complicated way of saying that, which I saved to the end, is basically that if you're going to perform a linear transformation, which means if you're going to multiply or add, whatever you add or multiply to your mean, whatever you're adding or multiplying your distribution by, you need to also multiply by the mean. That's what this fancy lettering says, right? This part says if you're adding or multiplying your distribution by some numbers, you don't need to worry about whatever you add, but you do need to worry about whatever you're multiplying by, right? So you take the absolute value of whatever it is you're multiplying by, multiply that by your standard deviation, and that'll give you your new standard deviation. The mean, you just do whatever you're doing to everything else, multiply and then add, and you'll get your new mean. But for your standard deviation, you just do multiplication, and you only do the positive value. If you're adding, then it doesn't change your standard deviation, so you don't have to worry about it. Now, it is possible to combine two random variables to make one new random variable. And it's actually not that complicated of a process. So for any two random variables, x and y, if t is going to be the new random variable, right, the combined random variable, then the expected value is just the two added together. That's convenient, right? So all we got to do is add the means, add the expected values together, and we get the new one. And then as long as they're independent, which they usually are, I don't think we look at a case where they're not. But as long as they're independent, then if we want to find the new variance, then we just add the old variances together. Now note that we're saying variance here. This does not apply to the standard deviations, right? It's kind of like Pythagorean theorem. You'd have to like square root everything to get the standard deviations, but that's fine. That's not that big of a deal, right? It's like, variance x squared, or standard deviation squared plus standard deviation squared equals standard deviation squared. A squared plus b squared equals c squared. So if you're good at geometry, this should be pretty straightforward for you. It's a very similar relationship. Now, if we're subtracting, right? If we're going to subtract two random variables from each other, then instead of adding the means together, we would subtract the means from one another. So that makes sense. However, we would still add the variances together because we're causing it to become more spread out than it already was. If you take two distributions that are together, right, especially if they're normally distributed, you can imagine if I remove one distribution out of it, then all the stuff that's left over isn't going to be as concentrated in the center, so it becomes more varied than it was before, even if there's less stuff. It's a weird thing, but just trust me on this. I don't really feel like showing you proof of this, but I'm sure there's a video somewhere out there that someone better than me made that can prove this for you. Basically, when you add two random variables, you add their means and add the variances to get the new mean and variance. If you are subtracting two random variables, you would subtract the two means to get the new mean, but you would still add the variances to get the new variance. And we're not going to look at when you multiply random variables with each other. We're not doing that. Now, visual example for this. So let's say that Pete and Aaron are going to combine their their companies together. So Pete's mean and standard deviation was 3.75 and 1.09. Aaron's business has a mean of 3.1 and 0.943. So if we want to find the mean and the standard deviation of the two of them together, then we would add these two means together, and we would square both the standard deviations and add the standard deviations together. So that's pretty easy. If instead Erin is branching out on her own from Pete and taking her business with her, then we would subtract the two means from each other, but we would still add the variances together after squaring the standard deviations. And again, it's pretty straightforward stuff. Now, I think it's a lot more interesting to look at combining random variables in the instance when they're continuous, right? This is a tricky problem that is similar to something that would come up on an AP test, right? This is the standard AP style problem. So Mr. Starnes likes between 8.5 and 9 grams of sugar in his tea. Suppose the amount of sugar in randomly selected packets follows a normal distribution with a mean of 2.17 and a standard deviation of 0.08. If he selects 4 packets at random, what's the probability his tea will taste right? Okay. Each one of those sugar packets is its own random variable because, on average, the mean of each sugar packet is 2.17 with a standard deviation of 0.08. So each one of these is its own continuous random variable. So when we add them all up, we're adding 4 kind of unique variables together. Also, 4 packets of sugar in your tea is too much. So what we'd have to do is say, okay, well, we have 4 different means, or 4 different sugar packets, each with the same mean. So we just add the 4 means together. So that's easy. 2.17 plus 2.17 plus 2.17 plus 2.17. That gives us our new mean, so 8.68. And then to find the new standard deviation, well, we can't just add 0.08 together 4 times. We have to square it and then add that value, so 0.064, add that together 4 times, and then take the square root of that. And when you do that, you'll get 0.16. So essentially, this is 0.08 squared plus 0.08 squared plus 0.08 squared plus 0.08 squared gives you 0.16, right? So we have to do that arithmetic, to find the new mean and the new standard deviation. It would be nice if we could just divide these by 4 and go from there, but it doesn't work that way. It would be nice, but it doesn't. We tried it. So now that we've done that, we can again either use the z-scores like we've done in the past, or we can do a normal CDF. using the calculator or one of our online calculators, right? So we know that it's between 0.85 and 0.68. So between 0.85 and 0.9 rather. If the mean is 8.68, there we go, and the standard deviation is 0.16. So the probability that his tea tastes right is 0.847 if you round it. So there's an 84.7% chance that he gets it right using 4 packets of sugar, which is probably why he uses 4 packets of sugar. So there you go. And here's the same thing done by hand. So that is everything about about random variable distributions. I know it's a lot in a short period of time, but it's pretty intuitive once you get used to it. Just keep going and it starts making sense, right? So none of this was super complicated. It all looked a bit weird at first, but thankfully, since it's using normal distributions and we're familiar with that, then it's nothing really new. It's either using the same one variable statistics that we did in the past, or it's using normal distributions, both of which should be familiar to us. So thank goodness, right? Anyway, I hope this was helpful.